All right, so let's look at graphing exponential growth functions, but let's really start and go over an exponential growth function itself. And so let's see, we've got a t, in other words, the amount we may have over time, and that could be in dollars, it could be in population, it could be in bacteria count, it could be in a lot of different things, whatever a may represent, equals a, the amount we begin with, times 1 plus our rate of growth raised to the power of t, or the number of years involved. So let's think about this as the amount over time equals the initial amount times 1 plus the rate of increase, since we're doing about growth, raised to the power of time, whatever time period we're talking about. And this part of the function we can consider to be our growth factor. All right, well, now let's look at this problem. Teen spending is expected to grow 3.5% annually from $79.7 billion in 2006. Draw a graph to show the spending growth. So let's get this thing plugged into our function. So we're still going to say that we got a of t. So that's our function. And if I want to graph that, this is what I'm going to, this y equals is going to equal a of t. And we started with an initial amount of 79.7, and that's in billions of dollars, times 1 plus. Now it's important that I convert that percentage to a decimal. So that's going to be 0. I'm going to move that decimal 2 places to the left. 0.035 now raised to the power of t. And, well, I guess actually while I'm here, I can go ahead and perform that math inside the parentheses. Then we would have 7.97 times 1.035 raised to our exponential power. All right, this little formula right here is important. We use it a lot for different things, anything that's involving exponential growth. The amount we're going to end up with equals an amount over time, in this case, equals our initial amount times 1 plus our rate of increase. That could also be our rate of decrease. But we're dealing right now in growth functions raised to the power of time. And there's no compounding. We'll learn about compounding, I think, a little bit later, or maybe in a different course. But that's an annual rate of return. All right, we're going to move over to the graph, and we're going to graph this thing and see what it looks like. It didn't ask us to predict. It just asked us to graph. We could predict from it, though, if we wanted to. All right, well, let's graph our growth function that we created from that data. And remember, we're talking about teen spending, and in 2006, it was 79.7 billion. And that's, so we're just going to use 79.7. We got to remember this is in billions of dollars, times 1 plus our growth rate, and our rate of increase, or 1 plus our rate of increase, which gives us our growth factor. And it was 3.5% annually, so that is 0.035. So our growth rate then is 1.035. Hope you follow that. Raised to the power of x, and x is really our time frame. So I'm going to go caret x. All right, so there's my function. But before I go look at it, I got some pretty large numbers in here. Maybe I want to think about my window settings. So I'm going to go to my window, and it's in my normal default mode. But remember now, we started at Well, we're talking about time. The x-axis is in time. It's a of t, so x-axis is in time. Well, time typically can't be negative, so I think I'll set that equal to 0. And x max. Well, I don't know. We want to look at a few years. We could put 10. We could put 15. Let's go 15 just for fun. We could put 10, but this, again, x is equal to number of years, so 15 years. We'll leave our scale at 1. Now, what about y minimum? Remember now we got an initial amount of 79.7 billion. So I think maybe I better set y at least equal to 0. 70. And I don't know, y max. I'm going to just arbitrarily... let's just double that amount. What do you think? We could go with 140. And then I need to think about my scale. What kind of scale should I use on that? Well, let's see. If I did 10, 70 between that, I could maybe do 10. Yeah, let's do a scale of 10. Now let's go see what our graph looks like. Almost looks linear, doesn't it? Let's go on our graph and let's go on our table and see what's happening. Let me see. So we scroll down here. Okay, I see that 0 in our 0 year, which would be 2006, we're looking at 79.7 billion. That looks good. After a year, 82.49. After 2 years, 85.37 or 38 billion. What about after 5 years? 5 years, we're up to 94.7 billion. How about 10 years? What about 10 years? 2016 in this case. 112.4 billion. We're currently in 2019, so let's look at 19 from 6, that'd be 15, right? 133.5 billion. Tell you what, I don't know whether to tell you to spend some more money or not. Maybe you need to save some.